Close your eyes. Breathe deeply. Let your mind drift beyond the ordinary, beyond what is known, and into the vast expanse of the unknown. There are questions, strange, perplexing, and endlessly fascinating, that no one has answered. Mysteries that linger at the edges of human understanding, teasing us with the promise of discovery, yet slipping further away the closer we reach. Imagine floating through the quiet darkness of space, where gravity ceases to pull, where time stretches and bends, and where light from distant stars carries secrets older than the Earth itself. Science has brought us remarkable knowledge, but even the greatest minds stand before certain questions with no answers, only speculation, only wonder. How does consciousness arise from mere atoms? Why is the universe expanding at an accelerating rate? What unseen forces shape the cosmos, guiding planets, stars, and galaxies along invisible threads of gravity? And then there are the deeper mysteries, those that lie not in the vastness of space, but within the fabric of reality itself. The quiet hum of the universe surrounds you. The air is still. In this moment, you are not just an observer of these mysteries, you are part of them. Let go of the need for answers. Sink into the beauty of the unknown, where every question is an invitation to dream. Tonight, we drift through the most puzzling scientific mysteries, secrets that have eluded discovery, riddles whispered by the universe. There is no rush, no urgency to solve them. Instead, let them wash over you like waves upon a silent shore. Close your eyes, breathe deeply, and surrender to the wonder of all that remains unanswered. The Pioneer anomaly, a spacecraft's impossible drift. The vastness of space is supposed to be predictable. Newton's laws, Einstein's equations, these mathematical rules define how objects move, how gravity pulls, and how momentum carries things forward. And yet, even within this precise system, there are mysteries. Unsettling deviations, silent whispers of the unknown. Among them is one of the strangest puzzles in space exploration, the Pioneer anomaly. It began with two spacecraft, Pioneer 10 and Pioneer 11. Launched in the early 1970s, these robotic explorers were sent beyond the planets, tasked with charting the outer solar system and venturing into interstellar space. They traveled for decades, moving precisely as expected, until they didn't. Scientists noticed something odd. A subtle, almost imperceptible force was acting upon them, slowing them down in a way that no known law of physics could explain. It wasn't a mechanical failure. It wasn't interference from a planet. It was something else. At first, the anomaly was dismissed as an observational error. Perhaps the tracking data was flawed, or the instruments weren't calibrated correctly. But as the years passed and the anomaly remained, the scientific community had to take it seriously. The effect was tiny, an unexpected deceleration of about 8.74 10 but it was persistent. Something was gently tugging at the Pioneers, something beyond calculation. One by one, explanations were proposed and discarded. Could it be gas leaking from the spacecraft? That didn't match the pattern of the drift. Could it be the sun's radiation pressure? The numbers didn't add up. Some suggested dark matter, an invisible force in space. Others whispered about unknown physics, deviations from Einstein's relativity, or forces from beyond our current understanding. To grasp the strangeness of the Pioneer anomaly, imagine throwing a ball in a perfectly controlled environment. No wind, no interference, just pure motion. Now imagine that ball, despite every calculation saying it should move in a straight line, begins to slow down mysteriously. Not because of friction, not because of gravity, but because of something else, something unseen, something outside our equations. That's what happened to the Pioneers. For years, NASA tracked them. Engineers and physicists scoured the data, trying to pinpoint the source of the deviation. Every known force in the universe was accounted for, yet the anomaly persisted. It was as if space itself was gently resisting the probes, as if some invisible hand was holding them back. Some theorists turned to new physics. Could this be evidence of a deviation from general relativity? Could it hint at a hidden force, a new fundamental interaction? If true, the implications would be staggering. A discovery like this could rewrite our understanding of gravity, space-time, and even the nature of reality. But not all explanations required rewriting physics. In the early 2000s, a more mundane answer emerged: heat radiation. The Pioneers, after decades in space, emitted thermal radiation unevenly. the spacecraft had large radioisotope thermoelectric generators, RTGs, which converted heat into electricity. This heat, slowly radiating out into space, might have acted as a gentle thruster, nudging the spacecraft ever so slightly. Simulations supported this idea. The heat didn't push the probes in a single direction, but over long periods, it created a subtle force, just enough to account for the anomaly. If correct, the mystery was solved. No new physics, no dark matter, just an overlooked effect of heat in the vacuum of space. And yet, some remain unconvinced. The thermal radiation explanation fits well, but it doesn't quite feel like the grand revelation many had hoped for. Some physicists still suspect that there may be more to the anomaly, something waiting to be uncovered. In a way, the Pioneer anomaly is more than just a scientific puzzle. It's a reminder of how much we don't know. Space, for all its silent emptiness, is not passive. It whispers secrets to those who listen. It presents mysteries, challenges, and questions that stretch the limits of our knowledge. Even if the mystery is fully solved, the lesson remains. What else are we missing? What other forces, unseen and unmeasured, might be acting upon our universe? The Pioneer anomaly may have been one of the first signs that our understanding of space isn't as complete as we once thought. As the pioneers drift further into the void, silent, ancient travelers beyond the reach of Earth, they carry with them the echoes of this mystery. Somewhere in the darkness, beyond the pull of the sun, beyond the edges of the known, they continue their journey. Not just as machines, but as reminders. Reminders that even in the vast cold emptiness, there are forces we do not yet understand. And perhaps, as you close your eyes and drift into sleep, your mind will follow them, out past the planets, past the stars, beyond the known laws of physics, out into the great unanswered questions of the cosmos, where even the smallest anomaly can change everything we believe to be true. The mpemba effect. Why hot water freezes faster than cold water is one of the most familiar substances in our daily lives. We drink it, we bathe in it, we cook with it. Yet it holds mysteries that still puzzle even the brightest scientific minds. Among these enigmas is one so counterintuitive, so strange that it continues to defy explanation. The mpemba effect, the phenomenon where hot water freezes faster than cold water under certain conditions. At first glance, this idea seems absurd. We instinctively believe that cold water should freeze first because it is already closer to freezing. This is what common sense and basic thermodynamics would suggest. And yet, throughout history, observations have repeatedly shown that, under certain circumstances, hot water can freeze faster than cold water. This paradoxical effect is named after Erasto Mpemba, a Tanzanian student who, in 1963, noticed this anomaly while making ice cream at school. His discovery would spark one of the longest-standing debates in physics and chemistry. The effect had been observed before. Aristotle mentioned a similar phenomenon over 2,000 years ago, and Francis Bacon and René Descartes noted it in their writings. But Mpemba was the one who brought it to the attention of modern science. His curiosity led to a formal investigation, and soon, researchers around the world were grappling with this perplexing reality. But why does this happen? Why would heating water somehow accelerate its journey to freezing? The question has led to countless experiments, each attempting to pin down the precise mechanism behind the mpemba effect. Over the years, multiple theories have emerged, but none have provided a definitive answer. One popular theory involves evaporation. Hot water evaporates more quickly than cold water, reducing its overall volume. With less water to freeze, it seems logical that the process might complete faster. But this doesn't fully explain the effect. Experiments have shown that even when evaporation is controlled, the mpemba effect can still occur. Another explanation revolves around supercooling. Normally, water freezes at 0 degree 32 degrees Fahrenheit, but under certain conditions, it can be cooled below that temperature without forming ice. This is called supercooling. Some scientists propose that hot water is less likely to supercool than cold water, meaning it can begin forming ice sooner. However, this idea alone does not fully account for the effect. A third possibility lies in convection currents, the movement of water due to differences in temperature. When water is heated, these currents distribute the heat unevenly, creating complex motion inside the container. This movement might influence how the water loses heat, allowing hot water to reach freezing temperatures in a unique and unexpected way. Then there's the role of dissolved gases. Cold water holds more dissolved gases like oxygen and carbon dioxide than hot water does. Heating water drives these gases out. Some researchers believe that the absence of these gases in hot water changes the way ice forms, possibly leading to faster freezing times. Could it be something even stranger? Some have suggested that the mpemba effect might be connected to the structure of water molecules at a microscopic level. Water isn't just a simple liquid. It has a complex network of hydrogen bonds that shift and reorganize based on temperature. Some believe that heating water might change these bonds in a way that speeds up freezing later. Yet, despite these many theories, no single explanation has been universally accepted. The mpemba effect remains elusive, behaving inconsistently depending on different conditions, such as the type of container, the surrounding environment, and even the purity of the water itself. The debate over the mpemba effect isn't just about one peculiar phenomenon. It challenges our understanding of heat transfer, phase transitions, and the very laws of thermodynamics. It's a reminder that even the most basic aspects of nature can still surprise us. Scientists continue to test and refine their hypotheses, but every experiment leads to more questions. Could the mpemba effect be tied to some yet undiscovered property of water? Could there be hidden variables at play that we haven't accounted for? For something as fundamental as freezing water, it's humbling to realize that we don't yet have all the answers. It's a testament to the beauty of science that even in the simplest things, there are still mysteries waiting to be unraveled. And so, as you drift into sleep, let your mind wander into the unknown. Imagine a world where the laws of physics are rewritten, where water dances between states in ways we can't yet comprehend. Let the unanswered questions pull you deeper, like ice forming in the stillness of night as you fade into the quiet embrace of dreams. The missing antimatter. Where did half the universe go? The universe is vast beyond comprehension, a seemingly endless expanse of stars, galaxies, and cosmic dust stretching in every direction. And yet, for all its immensity, the cosmos harbors a profound and unsettling mystery, one that has perplexed physicists for decades: the missing antimatter problem. According to everything we understand about the birth of the universe, there should be equal amounts of matter and antimatter. But when we look around, we see a universe dominated by matter alone. Where did all the antimatter go? To grasp the gravity of this mystery, we must journey back to the very beginning of time, to the moment of the Big Bang. Approximately 13.8 billion years ago, the universe erupted from an inconceivably dense and hot singularity, expanding outward in an explosion of unimaginable energy. In that first fraction of a second, particles began to form from pure energy, matter and antimatter, created in perfect pairs. This is the fundamental rule of particle physics. For every particle of matter, there must be an antiparticle with the opposite charge. When these two meet, they annihilate in a burst of energy. But here's the problem. If equal amounts of matter and antimatter were created in the Big Bang, then in the earliest moments of the universe, they should have completely canceled each other out, leaving behind nothing but pure energy, a universe empty of stars, planets, and life. And yet here we are. Something tipped the balance. Something somehow allowed matter to win. The universe should not exist as we know it, and yet galaxies swirl, stars burn, and life flourishes on a tiny blue planet in the vast darkness. This means that, against all expectations, somehow a tiny fraction of matter survived. But why? What happened to the missing antimatter? One possibility is that a fundamental asymmetry exists in the laws of physics, something that favors matter over antimatter. Physicists call this charge parity, CP violation, and it suggests that, under certain conditions, nature treats matter and antimatter slightly differently. If true, then in the early universe, these subtle differences may have led to a tiny excess of matter, just one extra matter particle for every billion particle-antiparticle pairs. Over time, as all the other pairs annihilated each other, that tiny excess of matter remained, forming the stars, planets, and galaxies we see today. But CP violation, as observed in experiments, is far too weak to account for the vast imbalance between matter and antimatter. If this were the only explanation, then the universe shouldn't be here, or at least, it should contain far less matter than it does. Something else is at play. Could antimatter still exist, hidden from our view? Some theories suggest that entire antimatter galaxies could be out there, separated from matter galaxies by vast cosmic voids. If such galaxies exist, we would expect to see telltale signs, gamma-ray bursts from occasional matter-antimatter collisions at the borders of these realms. Yet so far we have seen no such evidence. The universe appears overwhelmingly made of just matter. Another possibility is that antimatter decayed differently than matter in the early moments of the cosmos. Some theorists propose that exotic massive particles, known as leptogenesis particles, might have existed in the early universe and decayed in a way that produced more matter than antimatter. But such particles have never been observed directly, leaving this explanation speculative at best. Could antimatter have simply escaped? Some physicists speculate that during cosmic inflation, the rapid expansion that followed the Big Bang, matter and antimatter may have been flung into different regions of the universe. Perhaps antimatter was sent beyond our observable horizon, hidden in a realm we can never reach. If true, the universe may be symmetrical after all, just on a scale far beyond what we can detect. Then there's the idea that the laws of physics themselves might be incomplete. Some propose that a new force of nature, one we have yet to discover, acted upon antimatter differently than it did matter, creating the imbalance we see today. This would be revolutionary, rewriting our understanding of physics entirely. For decades, experiments have been designed to test these theories. The Large Hadron Collider, LHC, the most powerful particle accelerator on Earth, has searched for signs of new physics, hints of unknown forces or particles that could explain this mystery. So far, it has come up empty-handed. But physicists are not discouraged. They continue to probe deeper, refining their models, seeking answers in the smallest fragments of reality. The stakes are enormous. Solving the antimatter mystery could unlock new physics, revealing hidden aspects of the universe we never imagined. It might explain why we exist at all, why the delicate balance of nature allowed matter to triumph over annihilation. It could even hold the key to understanding dark matter, the invisible substance that shapes galaxies but remains elusive to direct detection. And so, as you drift into sleep, imagine a universe where things had gone differently. Imagine a cosmos where antimatter won the battle, where stars are built from antiprotons, where planets orbit around suns made of antihydrogen, and where civilizations, if they exist, are composed of anti-atoms, staring out at the sky in their own mirrored reality. But that is not our universe. In our reality, antimatter is missing. Its absence is a riddle written in the very fabric of existence, a puzzle without an answer, at least not yet. But perhaps somewhere out there in the farthest reaches of space, hidden beyond our reach, lies the missing half of creation, waiting to be discovered. And with that thought, allow yourself to sink into the vastness of the unknown. Let the mysteries of the cosmos carry you away as you drift into the quiet void of sleep, wrapped in the unanswered questions of the universe. The Great Attractor, a cosmic force pulling us in space, is vast beyond measure, a silent expanse stretching in all directions, filled with billions of galaxies, each one a collection of stars, planets, and cosmic dust drifting through the void. And yet, despite this infinite openness, there is something pulling us in, a force so immense that it is dragging entire galaxies, including our own Milky Way, toward it at staggering speeds. This unseen entity is known as the Great Attractor, and it may be one of the most mysterious forces in the universe. To understand this phenomenon, we must first acknowledge the movement of galaxies in the universe. The cosmos is not static. It is in a state of constant expansion, with galaxies moving away from each other due to the aftershocks of the Big Bang. However, the Milky Way, the Andromeda Galaxy, and thousands of others are not simply drifting outward. They are being pulled in a specific direction at a velocity of about 600 kilometers per second, 1.3 million miles per hour. Something enormous, something unimaginably powerful, is exerting an incredible gravitational influence on an entire region of space. But what is the Great Attractor? Where is it? What is it made of? And why can't we see it? The first hints of its existence came in the 1970s and 1980s when astronomers studying the cosmic microwave background radiation noticed that the entire local group of galaxies, including the Milky Way, was moving toward a specific region of the sky. This movement could not be explained by the normal expansion of the universe. Something, somewhere, was pulling us in. The problem? The Great Attractor is located in a part of the sky that is completely obscured by the zone of avoidance, a thick band of stars, gas, and cosmic dust at the center of our own galaxy. This means that, from Earth's perspective, we are unable to see directly into the region where the Great Attractor lies. It is hidden from view, a colossal force lurking in the cosmic shadows. Despite this, astronomers have been able to infer its existence by observing the way galaxies move around it. They have estimated that the Great Attractor is located about 150 to 250 million light-years away in the direction of the constellation Centaurus, at the heart of the Laniakea supercluster, the vast galactic neighborhood to which our Milky Way belongs. So what is causing this gravitational pull? Theories suggest that the Great Attractor is not a single object, but rather a concentrated region of mass formed by thousands of galaxies clustered together, creating a gravitational well that tugs on everything nearby. The Norma cluster, a dense grouping of galaxies, sits near the center of this region and is thought to be one of its most significant contributors. However, it does not account for all the gravitational force we observe, leading scientists to suspect that something even bigger, something beyond our current ability to detect, is at work. One possibility is that dark matter, the unseen substance that makes up most of the universe's mass, plays a major role. Dark matter does not emit, reflect, or absorb light, making it invisible to traditional telescopes. However, its gravitational influence can be detected in the motion of galaxies. If the Great Attractor is rich in dark matter, it could be exerting an enormous pull on surrounding galaxies, drawing them toward it like a cosmic whirlpool. But even dark matter might not fully explain this mystery. Some astronomers believe that the Great Attractor is only part of an even larger structure, a vast, supermassive region called the Shapley supercluster, located 500 million light-years away. This region contains more than 8,000 galaxies, packed together in a gravitational behemoth far larger than the Great Attractor itself. Some scientists now suspect that the Great Attractor is just a stepping stone, a waypoint in a much greater cosmic journey, with our galaxy ultimately being pulled toward the Shapley supercluster instead. If this is true, then our understanding of the universe's large-scale structure may need to be rethought. The idea that galaxies simply expand outward forever may not be entirely accurate. Instead, the cosmos may be shaped by a series of gravitational highways where entire clusters of galaxies are drawn toward massive unseen centers, some of which could be even bigger than anything we've ever imagined. But what does this mean for us? If the Great Attractor is pulling our galaxy in, does that mean we are on a collision course with something enormous? Will the Milky Way eventually be consumed by an unknown gravitational force? The answer is both reassuring and unsettling. While we are moving toward the Great Attractor, this process is unimaginably slow on human timescales. At a speed of 1.3 million miles per hour, it would take billions of years for any significant change to occur. Furthermore, by the time we reach it, the universe itself may have changed dramatically. The expansion of space could accelerate to the point where the Great Attractor's pull is no longer strong enough to affect us. Still, the fact that we are being influenced by an invisible force, one we cannot see but can feel, is a humbling reminder of how much we still do not understand about the cosmos. The universe is full of mysteries, forces we cannot explain, phenomena we can barely detect, and structures so vast they challenge the very limits of human comprehension. And so, as you drift into sleep, imagine yourself floating in the vast emptiness of space, being gently pulled forward by an unseen force. Picture galaxies swirling around you, slowly drifting toward something hidden, something massive, something that has existed for billions of years, waiting in the darkness. The Great Attractor is there, lurking beyond our vision, pulling us in ever so slightly, a silent whisper in the fabric of reality. It is a riddle written across the stars, a cosmic mystery that reminds us just how little we truly know about the universe. Let yourself sink into the unknown, drifting deeper into the mystery as you fall into sleep, embraced by the silent, eternal pull of the cosmos. Fast radio bursts, alien signals, or cosmic mystery. Space is filled with whispers. Some are the steady hum of cosmic background radiation, remnants of the Big Bang that echo across the universe. Others are the rhythmic pulses of neutron stars, ticking like celestial metronomes. But then there are the unexplained voices, the sudden, violent flashes of energy that appear out of nowhere, blaring across the radio spectrum before vanishing as quickly as they came. These are fast radio bursts, FRBs, brief yet incredibly powerful pulses of radio waves that originate from deep space. They last only a fraction of a millisecond to a few milliseconds, but in that blink of an eye, they can release as much energy as 500 million suns. The first fast radio burst was detected in 2007, completely by accident. Astronomer Duncan Lorimer and his student were analyzing old pulsar survey data when they stumbled upon an unusually strong and fleeting radio signal. It came from billions of light years away, and unlike anything previously observed, it appeared once and never repeated. At first, some scientists dismissed it as an anomaly, possibly a glitch in the data. But as years passed, more of these bursts were discovered. Now, FRBs are detected routinely, with thousands observed since that first mysterious burst. Some come from random, unknown sources, appearing once and never again. Others, however, are repeaters. They flash over and over again, following no predictable pattern, as if something deep in the cosmos is trying to send a message. But what is causing them? The power behind the burst. To truly grasp the mystery of FRBs, we must understand their unimaginable energy. A typical burst lasts for just a millisecond or less, but in that instant, it can outshine an entire galaxy in the radio spectrum. Imagine the most powerful explosion you can think of, an asteroid impact, a nuclear detonation, even a supernova. And now compress all of that energy into an instant so brief it is almost immeasurable. The energy involved suggests that FRBs must originate from extreme astrophysical environments, places where physics itself is pushed to its limits. But the problem is their unpredictability. Many FRBs are detected only once, vanishing forever before scientists can properly study them. Even the repeating FRBs refuse to follow a clear pattern, making it impossible to predict when the next burst will come. Theories. What's causing FRBs? Scientists have put forward several theories to explain FRBs, each more fascinating than the last. The most popular explanations include 1. Magnetars, the most extreme neutron stars. One of the leading theories suggests that FRBs come from magnetars, a type of neutron star with an insanely strong magnetic field. These fields are so intense that they can twist and snap violently, releasing bursts of energy in the form of radio waves. In 2020, astronomers detected an FRB coming from inside our own galaxy, linked to a known magnetar. This provided strong evidence that at least some FRBs originate from these ultra-dense, hypermagnetic remnants of dead stars. Number 2. Colliding neutron stars. Another possibility is that FRBs are caused by neutron stars colliding with each other. When two neutron stars spiral inward, their merging process releases an incredible burst of energy, potentially in the form of radio waves. This could explain one-off FRBs, but it doesn't account for the repeating bursts. The 3. Black hole interactions. Some scientists believe that FRBs could be linked to black holes, possibly from the material swirling around them, or even from small objects falling into them. If a neutron star were to fall into a black hole, the sudden distortion of its structure could release an intense blast of energy, detectable as an FRB. 4. Cosmic strings, remnants of the early universe. A more exotic theory suggests that FRBs could be the result of cosmic strings, hypothetical one-dimensional defects in space-time left over from the Big Bang. If these strings were to interact or snap, they could release bursts of energy in the form of radio waves. Number 5. Alien technology? Of course, no mystery in space is complete without the possibility of extraterrestrial intelligence. Some have speculated that FRBs could be signals from advanced alien civilizations, possibly created by massive interstellar beacons or propulsion systems. If an advanced civilization were using high-energy radio bursts to communicate or power their starships, it might look very similar to the FRBs we observe. However, there is currently no solid evidence supporting this idea. It remains an intriguing but speculative hypothesis, the mystery of repeating FRBs. One of the most puzzling aspects of FRBs is that some of them repeat. Unlike supernovae or neutron star collisions, which happen only once, certain FRBs flash again and again, sometimes after days, weeks, or even years. This strongly suggests that at least some FRBs are not caused by cataclysmic one-time events, but by a process that can occur multiple times. One of the most famous repeating FRBs is FRB 121102, located in a dwarf galaxy 3 billion light-years away. It has produced hundreds of bursts, showing that whatever is creating it is not being destroyed in the process. This has deepened the mystery. What kind of astrophysical object can create bursts of such enormous power yet remain intact? The future of FRB research. With each new discovery, the mystery of FRBs deepens. The next generation of radio telescopes, such as the Square Kilometre Array, SKA, and CHIME, will provide unprecedented sensitivity and resolution, allowing astronomers to detect FRBs in real time. By pinpointing their exact locations and tracking them with greater precision, scientists hope to finally uncover their true origins. Already, we have made significant progress. Some FRBs have been traced back to their home galaxies, offering clues about their environments. Others have been found clustering together, hinting at unknown cosmic structures that could influence their formation. The cosmic perspective. As you drift into sleep, imagine the vastness of the universe, the billions of galaxies scattered across an endless cosmic ocean. Somewhere, light-years away, an invisible radio pulse erupts from a hidden source racing toward Earth at the speed of light. It has traveled across time and space, crossing vast distances before finally reaching our telescopes as a brief, unexplained whisper in the void. What was its origin? A dying star twisting under magnetic pressure? A black hole tearing through the fabric of space-time? Or something else entirely, something we are not yet ready to understand? The mystery of FRBs reminds us that the universe is still filled with the unknown. We are only beginning to scratch the surface of its deepest secrets. As you close your eyes and drift off, let yourself sink into the mystery of the cosmos, into a reality where signals from the stars whisper in the darkness, waiting to be deciphered. The placebo effect. Can the mind heal the body? The human mind is a mystery greater than any scientific enigma. It is capable of generating thoughts, emotions, and even entire realities that exist only within the vast network of neurons and electrical impulses. But what if the mind holds more power than we realize? What if it can heal the body, not through medicine, surgery, or technology, but purely through belief? This is the placebo effect, one of the most baffling and paradoxical phenomena in medical science. It occurs when a person experiences real improvements in their health after receiving a fake treatment. A sugar pill, a saline injection, or even just a reassuring word from a doctor, simply because they believe they are receiving something effective. At first glance, the placebo effect seems impossible. How can the mere belief in a treatment produce real, measurable changes in a person's health? How can expectation alone influence symptoms, pain, and even disease progression? Scientists have been studying this phenomenon for decades, and while many insights have been uncovered, one fundamental question remains unanswered. How much of healing is controlled by the mind rather than the body? The power of expectation. Why the placebo effect works. Expectation is a powerful force. When a person believes they are receiving a powerful medicine, their body often responds as if they actually had. This happens because the brain doesn't just passively process experiences, it actively creates them. If you expect relief from pain, your brain may release endorphins, the body's natural painkillers. If you expect relaxation, your nervous system may reduce stress hormones. The brain acts as a self-fulfilling prophecy machine, shaping reality based on expectations. Studies have shown that even the appearance of a placebo treatment matters. A red pill can be more stimulating than a blue pill. Larger pills seem stronger than smaller ones. Injections work better than pills, and surgical procedures, even fake ones, can have an even stronger placebo effect. The more elaborate and convincing the treatment appears, the greater the effect it produces. The body follows the script written by the mind, even if that script is based on a lie. The neuroscience of healing, the brain's pharmacy. To understand how the placebo effect works, we need to dive into neuroscience. When a person takes a placebo, several things happen in the brain. 1. Pain perception changes. The brain releases endorphins, which act on the same receptors as opioid painkillers. People who take placebo painkillers experience real reductions in pain, often indistinguishable from the effects of actual medication. 2. Dopamine floods the brain. In conditions like Parkinson's disease, placebo treatments have been shown to increase dopamine levels, temporarily improving movement and reducing symptoms. 3. Stress and anxiety decrease. Placebos trigger activity in the prefrontal cortex, which helps regulate stress and anxiety. This is why placebos can be as effective as antidepressants for some people. 4. Immune system changes. Incredibly, placebos can also influence the immune system. In some cases, patients with immune disorders have shown improvement after taking a placebo, suggesting that the brain can signal the body to enhance its defense mechanisms. The placebo effect is not just psychological, it has measurable biological effects that demonstrate how powerful the mind can be in influencing the body. Placebos in medicine, more than just a trick? For centuries, doctors unknowingly relied on the placebo effect. Before the advent of modern medicine, many treatments were useless or even harmful, yet some patients still recovered. Whether it was a healing ritual, an herbal remedy, or a doctor's comforting words, the belief in treatment was often more powerful than the treatment itself. Even today, doctors sometimes use placebos in clinical settings. In some cases, patients with no other treatment options have been given placebos, and some experience genuine improvements. The ethics of using placebos are debated. Should doctors deceive patients if it might help them? But the undeniable fact is that the placebo effect works, even when people know they are receiving a placebo. One of the most fascinating discoveries is that even when patients are told that they are receiving a placebo, they still experience benefits. This suggests that the act of treatment itself, going to a doctor, receiving a pill, engaging in a healing process, triggers deep psychological and physiological mechanisms that promote recovery. The nocebo effect. When belief makes you worse. If the placebo effect can heal, its dark twin, the nocebo effect, can do the opposite. This occurs when negative expectations cause harm or worsening symptoms, even when no real threat exists. For example, in drug trials, patients who take sugar pills sometimes report severe side effects simply because they expect them. Some people who believe they are allergic to a substance experience real physical reactions when given a harmless substitute. A patient who is convinced they have a deadly illness might actually develop real symptoms, driven purely by anxiety and expectation. The nocebo effect is a chilling reminder of how much control the mind has over the body, not only in healing, but also in suffering. The limits of the placebo effect. Can it cure disease? As powerful as the placebo effect is, it has limits. It can reduce pain, improve mood, and even influence immune function, but it cannot cure cancer, regenerate lost limbs, or reverse severe physical damage. The placebo effect is most effective for symptom relief, pain, nausea, fatigue, anxiety, but it does not remove tumors or heal broken bones. That being said, harnessing the placebo effect could revolutionize medicine. If doctors could enhance placebo responses alongside real treatments, it could lead to lower drug dosages, fewer side effects, and improved overall health outcomes. Can we control the placebo effect? One of the biggest questions in placebo research is whether we can consciously activate it. If belief alone can heal, could people train themselves to trigger placebo responses without external treatments? Some researchers believe that meditation, visualization, and positive thinking could enhance the body's natural placebo mechanisms. Studies on people who practice mindfulness and self-hypnosis show that they can reduce pain, manage stress, and even alter immune responses. A universe of possibilities, the mind's hidden power. As you drift off to sleep, consider this. If the mind can trick the body into feeling pain relief, reducing anxiety, or even activating immune responses, what else might it be capable of? Could we one day unlock the full potential of belief-driven healing, learning to control our own physiology as effortlessly as breathing? The placebo effect is a glimpse into the immense, untapped power of the brain. It reminds us that healing is not just about medicine, but about perception, expectation, and the profound connection between the mind and body. Perhaps the greatest frontier in medicine is not the search for new drugs or surgical techniques, but the exploration of our own innate ability to heal. For now, the mystery remains unsolved. But as science continues to explore the unseen forces within us, one thing is clear. The mind is far more powerful than we ever imagined. Consciousness, the greatest mystery of the mind. Consciousness is the most intimate experience we have, yet it is also the greatest mystery of existence. We live every second of our lives inside the theater of our own awareness, seeing, hearing, thinking, feeling. But no one truly understands how or why we experience reality the way we do. How does the brain, a 3-pound mass of neurons and electrical impulses, generate the feeling of being alive, of having thoughts, emotions, and a sense of self? Why is it that we are aware of the world, rather than simply reacting to it like machines? Despite all the progress in neuroscience, no one has fully explained what consciousness is or where it comes from. Many theories attempt to unravel this mystery, but none have provided a definitive answer. Some believe that consciousness arises purely from the brain, an emergent property of billions of neurons firing in complex patterns. Others speculate that consciousness might be a fundamental part of the universe, existing beyond mere biology. Could it be that our awareness is not just a byproduct of evolution, but something deeper, something woven into the very fabric of reality? The hard problem of consciousness: why do we feel? One of the greatest challenges in understanding consciousness is what philosopher David Chalmers called the hard problem of consciousness. Science can explain how the brain processes information, how neurons communicate, and how different regions of the brain control thoughts and emotions. But what it cannot explain is why any of this results in experience, why the firing of neurons produces the feeling of pain, the sensation of color, or the emotion of love. Consider a computer. It can process vast amounts of data, recognize patterns, and even simulate human conversation, but it does not experience what it is doing. It does not feel happiness, sadness, or curiosity. Even the most advanced artificial intelligence remains a lifeless system devoid of self-awareness. So why is the human brain different? Why do we have a first-person perspective, a private, internal world that no one else can access? Theories of consciousness. Is the mind more than the brain? Scientists and philosophers have proposed many theories to explain how consciousness arises. Some of the most prominent include: 1. The neural correlates theory. This idea suggests that consciousness is directly tied to specific patterns of neural activity. If we can map the brain precisely enough, we may discover what makes some brain activity conscious and others unconscious. 2. The global workspace theory. This theory proposes that consciousness emerges when different parts of the brain share information across a global network, much like multiple computers linking together to form a single system. 3. Panpsychism. A more radical theory, panpsychism suggests that consciousness is a fundamental property of the universe, much like space, time, or gravity. According to this view, everything, even atoms and electrons, might have some basic form of awareness. Number 4. Quantum consciousness. Some scientists, like physicist Roger Penrose, speculate that consciousness arises not from traditional neural activity, but from quantum processes occurring inside the brain's neurons. This theory suggests that our awareness may be linked to the fabric of reality itself. The illusion of free will. Are we really in control? One of the strangest implications of consciousness research is the possibility that free will might be an illusion. Neuroscientists have discovered that the brain makes decisions before we are even aware of them. In some experiments, brain activity predicting a choice occurs milliseconds before the person reports making the decision. This suggests that what we think of as a conscious decision might actually be the brain deciding first, with consciousness simply justifying the choice afterward. If this is true, then who or what is actually in control? Are we merely passengers inside our own minds, watching as our brain makes choices for us? If free will is an illusion, does that mean our sense of self is also an illusion? And if so, what does that say about consciousness itself? Dreams and altered states, the shape-shifting nature of awareness. If consciousness is a stable, continuous experience, then why does it change so dramatically when we dream? Why do we sometimes lose awareness under anesthesia, only for it to return as if nothing happened? These shifts in consciousness raise even more questions. When we dream, we enter a world that feels just as real as waking life, yet it is entirely constructed by the brain. What does this say about the nature of reality? During deep sleep, our consciousness vanishes completely, yet we wake up the next day as if no time has passed. Where does consciousness go? Psychedelic substances can completely alter the nature of self-awareness, leading some to experience a sense of unity with the universe. Are these hallucinations or glimpses of a deeper truth? If our perception of reality can shift so easily, what does that mean for our normal waking consciousness? Could it be just another form of illusion? Consciousness beyond the brain? Could awareness exist without a body? If consciousness is purely a product of the brain, then when the brain dies, consciousness should cease to exist. But what if it doesn't? Some researchers have explored cases of near-death experiences, NDEs, where people who were clinically dead without a heartbeat or brain activity report vivid experiences of floating above their bodies, moving through tunnels of light, or meeting deceased loved ones. Could these be hallucinations caused by a dying brain, or do they suggest that consciousness can exist independently of the body? Additionally, many religious and spiritual traditions suggest that consciousness is eternal, surviving death in some form. While science has yet to find evidence for this idea, the fact that consciousness itself remains unexplained leaves open the possibility that it could extend beyond the physical realm. A final mystery. Will we ever understand consciousness? As you close your eyes and drift into sleep, consider this. Everything you've ever known, every thought, feeling, and experience has existed only within your consciousness. The world outside may seem real and tangible, but you have never actually touched it directly, only the version of it your mind has created. Science has uncovered incredible truths about the universe, about black holes, quantum mechanics, and the origins of life. But it still cannot answer the most personal, fundamental question of all. Why are you aware? Perhaps consciousness will forever remain a mystery, an unsolvable paradox that no amount of science can fully explain. Or perhaps one day, we will discover that the mind is far more powerful and mysterious than we ever imagined, a force that stretches beyond the brain, beyond biology, and into the deepest unknowns of existence. Dark matter, the hidden mass of the universe. The universe we see, the stars, planets, and galaxies shining brightly in the night sky, represents only a tiny fraction of what actually exists. Most of the universe is invisible. In fact, about 85% of the total mass of the universe is missing from our direct observations. We can't see it, touch it, or detect it in any traditional way, yet its gravitational influence is undeniable. This invisible substance has been named dark matter, a mysterious form of mass that refuses to interact with light but shapes the very structure of galaxies and the cosmos itself. Despite decades of research, scientists still have no idea what it is. Could dark matter be an unknown type of particle? Could it be something beyond our current understanding of physics? Or is it possible that our theories of gravity themselves need to be rewritten? The discovery of dark matter, a cosmic mystery, unfolds. The first clues that something unseen was lurking in space came from observations of galaxies in the early 20th century. Astronomers expected that stars near the edges of a galaxy would orbit more slowly than those near the center, just as planets in the solar system orbit the sun at different speeds based on their distance. However, when the astronomer Vera Rubin studied the rotation of galaxies, she found something baffling. The outer stars were moving just as fast as the inner ones, defying Newtonian physics. There was extra gravity holding them in place, but no visible mass to explain it. The only explanation was that a huge amount of invisible mass, something that didn't emit or reflect light, was scattered throughout galaxies, providing the extra gravitational pull needed to keep them spinning at those speeds. This was the first major evidence that dark matter existed. The cosmic web, how dark matter shapes the universe. Dark matter is not just a small, local anomaly, it's everywhere. Scientists now believe that dark matter forms a vast cosmic web, an invisible skeleton that holds galaxies and galaxy clusters together. Without dark matter, the universe as we know it couldn't exist. Computer simulations suggest that shortly after the Big Bang, dark matter acted as the first scaffolding, pulling normal matter together into dense pockets where stars and galaxies could form. Without this unseen force, galaxies would have never clumped together, and the universe might have remained a thin, structureless mist of gas. In many ways, dark matter was the silent architect of the cosmos, shaping the universe in ways we are only beginning to understand. What is dark matter made of? Despite its enormous influence on the universe, scientists have no idea what dark matter actually is. Since it doesn't interact with light, we can't see it directly, which makes it incredibly difficult to study. However, many theories have emerged about its possible nature. 1. Weakly interacting massive particles, WIMPs. One of the leading theories suggests that dark matter is made of exotic particles that barely interact with normal matter, except through gravity. These particles, if they exist, would pass through Earth and our bodies, undetected. 2. Axions. Another possible candidate is the axion, a strange, ultralight particle that might behave more like a wave than a traditional particle. If axions exist, they could explain many of the strange properties of dark matter. 3. Primordial black holes. Some researchers speculate that dark matter might not be a particle at all, but instead could be made up of tiny black holes that formed in the early universe. These black holes would be invisible unless they swallowed up matter, which could explain the gravitational effects we observe. 4. Modified gravity. A more radical idea suggests that dark matter doesn't exist at all, and that the problem lies in our understanding of gravity. Some physicists argue that we need to rewrite the laws of gravity to account for the strange motion of galaxies without needing dark matter. Dark matter versus dark energy. Two different mysteries. It's easy to confuse dark matter with dark energy, but they are completely different mysteries. While dark matter makes up about 27% of the universe, dark energy makes up nearly 70%, an even larger mystery that is causing the universe to expand at an accelerating rate. Dark matter pulls things together with gravity, helping galaxies form and stay intact. Dark energy, on the other hand, pushes things apart, stretching space itself and causing the cosmos to expand faster and faster. Both are invisible, both are poorly understood, and together they make up 95% of the universe. In other words, almost everything we know about reality comes from the remaining 5%. The small fraction that consists of normal matter like stars, planets, and us. Searching for dark matter. How do we find the invisible? Since dark matter doesn't emit or reflect light, detecting it directly is incredibly challenging. However, scientists have developed several methods to try and uncover its true nature. Underground detectors. Huge tanks filled with liquid deep underground are used to detect rare interactions between dark matter and ordinary matter. If a dark matter particle ever collides with an atomic nucleus, these detectors might catch the signal. Particle colliders. The Large Hadron Collider, LHC, smashes particles together at nearly the speed of light, hoping to create dark matter particles or find traces of their existence in the debris. Astronomical observations. Scientists study how galaxies move and how light bends around them to infer the presence of dark matter. The way light from distant galaxies gets distorted, a phenomenon called gravitational lensing, suggests there's an unseen mass bending spacetime. Gamma-ray signals. Some researchers believe that dark matter particles might annihilate each other and produce faint bursts of energy, detectable as gamma rays. Space telescopes like NASA's Fermi telescope are searching for these signals. What if we never find dark matter? If dark matter remains undiscovered, it could mean one of two things. Either we aren't looking in the right way, or our entire understanding of the universe is flawed. Some physicists argue that dark matter might be a placeholder for something deeper, a symptom of a more fundamental problem in physics. If we never find dark matter, scientists may be forced to rethink gravity itself, possibly leading to a new revolution in physics. Just as Einstein's theory of relativity changed our understanding of space and time, the hunt for dark matter could lead to discoveries that completely transform our knowledge of the cosmos. A universe of shadows, living in the unknown. As you drift into sleep, think about this. The universe you see is not the universe that exists. Everything we know, stars, galaxies, black holes, planets, is only a small fraction of reality. Most of the universe is missing, hidden in a form we can't touch or see, a force that shapes the cosmos yet remains completely invisible. Perhaps dark matter will one day be understood and its secrets unlocked. Or perhaps it will remain forever beyond our grasp, a ghostly presence woven into the fabric of reality. Either way, as you close your eyes and let your thoughts wander, remember this: the greatest mysteries of the universe are still out there, waiting to be uncovered. Dark energy, the force expanding the universe faster. The universe is not just expanding, it is accelerating, stretching outward at a rate that defies all expectations. This revelation shattered everything we thought we understood about cosmology, introducing one of the greatest mysteries in physics: dark energy. Unlike gravity, which pulls objects together, dark energy seems to be doing the opposite, forcing galaxies apart at ever-increasing speeds. It is invisible, undetectable, and yet it makes up nearly 70% of the entire universe. What could this strange, unseen force be? Scientists first discovered dark energy in the late 1990s while observing distant supernovae. These exploding stars served as cosmic mileposts, allowing astronomers to measure how fast the universe was expanding in the past. But to their astonishment, they found that the expansion wasn't slowing down as expected. It was speeding up. Something was pushing space itself outward, and no known force could explain it. This discovery sent shockwaves through the scientific community, leading to a fundamental rethinking of the universe's fate. One of the most perplexing aspects of dark energy is how it remains completely undetectable, except for its effects on cosmic expansion. Unlike dark matter, which at least interacts through gravity, dark energy doesn't clump together or exert force in any measurable way. It simply exists. If we could bottle it, it would be the most powerful energy source in existence, but its very nature is elusive. Some theories suggest that dark energy is a property of space itself, an intrinsic force woven into the very fabric of reality. Others propose that it might be a new, undiscovered field that permeates the cosmos, much like an invisible ocean stretching across infinity. Einstein himself had once proposed a similar idea. In his equations for general relativity, he introduced a term called the cosmological constant, a force that counteracted gravity to keep the universe static. When it became clear that the universe was actually expanding, Einstein dismissed it as his biggest blunder. Yet, decades later, scientists realized that something akin to Einstein's cosmological constant might be real after all, an energy infused into space itself, driving the acceleration of the universe. But why does dark energy exist, and why is it so finely tuned? If its strength were even slightly different, the universe could have torn itself apart before galaxies ever formed, or collapsed back in on itself long ago. This strange balance suggests something profound. Either we live in an exceptionally lucky universe, or there's a deeper law of physics we have yet to uncover. Some scientists even speculate that dark energy could be a clue to the existence of multiple universes, each with different properties. There is also the unsettling possibility that dark energy might not remain constant forever. If it were to grow stronger over time, it could eventually rip apart everything, including galaxies, stars, planets, even atoms themselves. This doomsday scenario is known as the Big Rip, where the expansion of the universe accelerates so violently that all matter is torn apart. On the other hand, if dark energy weakens, it could cause the universe to slow down and collapse in a final big crunch. Despite decades of research, we still have no definitive answers. Some theories suggest that dark energy could be a new, unknown particle, one that interacts with space in a way we cannot yet measure. Others propose that our understanding of gravity itself might be flawed, and that dark energy is merely the result of a deeper, hidden physics. Could it be a force from another dimension? A sign that the fabric of reality itself is shifting? One of the most tantalizing possibilities is that dark energy is linked to the quantum vacuum, the bizarre, fluctuating energy of empty space. In quantum mechanics, even the emptiest vacuum is not truly empty. It teems with virtual particles popping in and out of existence, creating a sea of energy that, in theory, could drive cosmic expansion. Yet, when physicists try to calculate this vacuum energy, their predictions overshoot the actual observed effect by an almost unimaginable factor, 10 form string times larger than expected. This staggering mismatch is one of the greatest unsolved problems in physics. Another mystery is whether dark energy has always existed or whether it switched on at some point in cosmic history. Observations suggest that in the first few billion years after the Big Bang, the universe's expansion was slowing down under gravity's pull. Then, suddenly, dark energy took over, accelerating expansion as if some hidden mechanism had been triggered. Could it be that dark energy is not a constant force, but something that evolves over time? If so, what could change it?